The 5,000-degree milestone. The European Space Agency just confirmed that the Euclid telescope has mapped 5,000 square degrees of the deep universe. This landmark represents 35% of the total mission and creates the largest high-resolution survey of dark matter in human history. The early data shows a structural divergence that suggests the cosmic web is clumping in ways that current physics cannot explain. We are seeing a map that does not match the math. This specific milestone is the trigger for a new citizen science effort called Space Warps, which launched this month to help humans identify the gravitational lenses that Euclid is finding faster than our algorithms can process. These lenses are the only way to weigh the invisible architecture holding the universe together. This mass measurement reveals a major problem with our understanding of cosmic growth: weighing the ghost in the machine. Euclid works by measuring a phenomenon called weak gravitational lensing. Think of it like looking at a street lamp through a piece of wavy glass. The light from distant galaxies is slightly distorted by the gravity of invisible dark matter sitting between them and the telescope. By processing 100 gigabytes of data every single day, Euclid can reconstruct exactly where that dark matter is hiding. The precision is high enough to see how these clumps have evolved over 10 billion years. This is not just a picture but a density map of the universe. In May 2026, researchers used this data to confirm the discovery of candidate Dark Galaxy 2. This is a ghost galaxy where 99% of the mass is dark matter with almost no stars to mark its location. This proves that dark matter is capable of clumping into small, isolated pockets, which challenges the idea that it only exists in massive halos around bright galaxies. This granular detail is where the standard model begins to fail. The tension that won't disappear. Cosmologists are currently facing what they call the S8 tension. This is a measurement of how clumpy the universe is today compared to how clumpy it should be based on the radiation left over from the Big Bang. The final analysis from the Dark Energy Survey published in early 2026 confirms that the modern universe appears smoother than the early universe predicted. However, Euclid's new high-resolution maps are showing a different kind of clumpiness at smaller scales. It is as if the universe is ignoring the speed limit of growth set by the standard model of cosmology. If the matter is clumping faster or slower than predicted, then our fundamental theory of gravity might be wrong at large scales. Some theorists argue this is just a measurement error, but the sheer volume of Euclid's data is making that excuse impossible to maintain. We are no longer looking for a missing piece of the puzzle. We are looking at the wrong puzzle entirely. The limits of general relativity. The standard model of cosmology assumes that dark energy is a constant, and that gravity behaves the same way across billions of light years. But Euclid's map shows that the connections between galaxy clusters and the cosmic web are far more intricate than our simulations allow. It is the equivalent of a structural engineer finding that a bridge is holding weight despite having no support beams where they should be. If Euclid continues to show this clumping discrepancy, it suggests that dark energy might change over time, or that Einstein's general relativity needs a massive update for low-density environments. This is a strategic crisis for physics, because every mission we launch is built on these assumptions. We are reaching the point where the mission is revealing the limits of our own intelligence. The signal under the noise. The 5,000-degree map and the discovery of objects like candidate Dark Galaxy 2 prove that we are measuring the failure of our current physics models in real time. We are moving beyond the era of refining the standard model and into the era of replacing it entirely. Because Euclid has confirmed that dark matter can cluster in ways that contradict the smooth predictions of the cosmic microwave background, the implication for the aerospace and science community is clear. We can no longer rely on universal constants to plan for the long-term mapping of the high redshift universe. For anyone tracking the mission, the real verdict arrives on October 21, 2026, with the release of Data Release 1. That will be the first comprehensive cosmology dataset that covers enough volume to officially confirm or kill the standard model. Until then, watch for the quick Data Release 2 on June 24th. That release will focus on the galactic bulge and will likely provide the final clues about how dark matter behaves at the center of our own home. The map is finally being filled in, and the results are brilliantly chaotic. Subscribe for more.